today we will try to solve two problems. The problem number 2 is, in a Rankine cycle, the maximum pressure of the steam supplied is 6 bar. The dryness fraction is 0.9. The exhaust pressure is 0.7 bar. So we have to find out the work done and the Rankine efficiency. So from TS and HH diagram, you can say we consider that 1, 2 is the pumping process, but we consider that from 1 to 3 that process is for the heat addition, that is Q in the boiler, and the process 3, 4 is the expansion process in the turbine, and that is W out, and process 4.1 is the condensation process, and the cycle repeats. So this point 3, in point 3, x equal to, we call it x3 equal to 0.9. That means dryness fraction is 0.9, and this line is x equal to 1, saturated dry steam line. And in HS diagram, point 3 is at the entry of the turbine, and point 4 is the exhaust of the turbine. And for point 3 the pressure is P3, which is given as 6 bar pressure, and point 4 is the exhaust pressure, or you can say the condenser pressure also, and that is equal to 0.7 bar pressure. So the steam enters the turbine at point 3. We need to calculate the values of H3 also. So from steam table you can find out this value. Say this is for actually point 3. Point 3 is 6 bar pressure. Point 3 is for 6 bar pressure, and this is for point 4 in the TS and HS diagram, and this is for 0.7 bar pressure. Accordingly, if we use the steam table, from steam table we can find these values. The sensible heat HF equal to this much, and the latent heat of evaporation equal to HFG equal to this one. The entropy of liquid is equal to this one, and entropy during the latent heat of evaporation equal to this one, HFG. And similarly, the corresponding values for 0.7 bar are this one, SF, SFG, HF, and HFG. This we can get from the steam table. Please refer a steam table to get this value for 6 bar pressure and for 0.7 bar pressure. So at point 3 we need to find out, we know that work done, work output is equal to heat drop from H3 to H4. So H3 minus H4 will give out us the work output, and in this case H3 is equal to, the condition of steam is wet steam, so that is equal to HF for this 6 bar pressure plus X3, the dryness fraction of steam at point 3, multiplied by HFG, latent heat of evaporation at 6 bar pressure. So if we put the values, HF equal to 670.4 kilojoule per kg plus X3 equal to 0.9 dryness fraction of steam at point 3, and HFG equal to 2085 kilojoule per 5.1 kilojoule per kg. And if we do the calculation, it is equal to 0.99 kilojoule per kg. And next we have to find out the value of H4. The value of H4 is again is equal to HF at 0.4, that means for 0.7 bar pressure, plus x4 for 0.4, the dryness fraction of steam, multiplied by HFG at 0.4. But in this case, we know the value of HF, that is equal to this much, and HFG equal to this much, but we do not know the value of x4, that is dryness fraction of steam at 0.4. So if we look at the TS diagram, we can see that process 3-4 is isentropic process, and therefore S3 is equal to S4. That means entropy of at 0.3 is equal to entropy at 0.4. So isoentropy, a process is isentropic process. So let us calculate from this equation S3 is equal to S4, and we know S3 is equal to again SF at 0.3 plus X3 into SFC at 0.3 is equal to, actually this is 4.3, this is also 4.3, is equal to S4. S4 equal to SF at 0.4 plus X4, dryness fraction at 0.4, multiplied by SFG at 0.4. So if we put the value that we have just got from the steam table, then this is equal to 1.931 plus 0.9 into, so these are the values we got. From these values we will find the value of x4. 0.9 into 4.827 is equal to 1.192 plus x4 multiplied by 6.288. If we simplify this, we will get the value of x4 is equal to 0.808, and that is equal to, say, we will consider it as a 0.8. By this equation we get the value of x4. x4 is the dryness fraction of steam at 0.4. That means we get the dryness fraction of steam at this point, or we can say at this point also, which is equal to x4. So now we can find out the value of H4. So H4 will be equal to H4 equal to HF. The value of HF already we got it from the steam table, that is equal to 276.2 plus X4, dryness fraction is 0.8, just now we have calculated, multiplied by 2283.3, and this calculation, if we complete it, we'll get 2202. Please check the calculation yourself. I may be wrong in my calculation. Kilojoule per kg. So this way we have find out the value of H4 also. The work done by the turbine or work output is done during the expansion process 3-4 from H3 to H4. So we have calculated H3 as well as H4. So W out is equal to H3 minus H4. So this way we will now find out the value of W out, work output. So work output is equal to H3 minus H4, and that is equal to 2546.99 minus 2202.84. that means this value, and that is equal to 344.15 kilojoule per kg. So this much of work is done by the turbine per kg of steam consumed. Now we have to find out the efficiency of the Rankine cycle. Efficiency of the Rankine cycle, and that is equal to work output divided by heat input, we say Q in, and Q in is equal to heat input in the turbine. Heat input is equal to Q in is equal to H3 minus H1, and we neglect this process. We consider that whole amount of heat is supplied in the boiler itself, so that is equal to H3 minus H1. H3 we know, but we have to find out the value of H1. That means at this point what is the amount of enthalpy, and that we know that is equal to HF. This value we call HF. In terms of enthalpy we will call it HF, sensible heat. To find out Q in we need H1, and H1 is equal to HF at point 1, or we can say HF1, and that value is equal to, we got it from, for 0.7 bar pressure, same pressure in the condenser pressure, that is equal to H1 equal to 376.2 kilojoule per kg. If that is so, now we can find out Q in. In is equal to H3 minus H1, and that is equal to H3 is 2546.99 minus 376.2, and this is equal to 2170.79 kilojoule per kg of steam. This is Q in. So we can now find out the Rankine efficiency, W out, which is equal to 344.15, and Q in is equal to 2170.79. So if we calculate it, will be is equal to 0.1536, or also we can say 15.36%. So that is the efficiency of the cycle, or Rankine efficiency you can say. And work done, we have calculated this much kilojoule per second, and that was the problem, to find the work done, that is theoretical work done, and the Rankine efficiency. So this way you can solve the problem. There may be some mistakes in the calculation, but you can check it by using your own calculator. Let us solve another problem, that is dry saturated steam at 20 bar pressure is supplied to a steam engine, steam turbine also it may be. The exhaust takes place at 1.3 bar. We have to calculate the Rankine efficiency and also the power developed if the feed water or steam consumption we can say is equal to 45 kg per second. From 1 to 3, that is equal to Q in, heat supplied in the boiler, 3 to 4 expansion in the turbine, 4 to 1 is heat rejection in the condenser. This is TS diagram. This line is x equal to 1. And this case x3, the drainage fraction of the steam at point 3 is equal to 1, because it is given that the dry saturated steam at 20 bar pressure, that means the steam entering into the turbine is, a turbine or heat engine is dry saturated steam. So similarly this is x equal to 1. P3 pressure is equal to 20 bar pressure, and P4 condenser pressure equal to 1.3 bar. So from 3 to 4 there will be heat drop. So W out, work output equal to H3 minus H4. You can write from steam table, say first at 20 bar pressure we get some values. We need actually Hg, dry saturated steam enthalpy, 2798.3 kilojoule per kg. If you refer on steam table, you should get this value. And at the same pressure, the entropy Hg of dry saturated steam is equal to 6.339 kilojoule same. Again at 1.3 bar pressure, that means condenser pressure. So again from steam table, now at 1.3 bar pressure, you have to take 4 values from this for this pressure, and first one is say SF entropy is equal to 1.386 kilojoule per kg per Kelvin. Then again SFG is equal to 846 kilojoule per kg per Kelvin. Similarly HF enthalpy is equal to 449.19. I take these values from one steam table. You can also refer one steam table. So HFG is equal to 2237.5 kilojoule per kg. So again you refer the TS diagram. So in this TS diagram again we can see process 3-4 is isentropic process. So S3 is equal to S4 isoentropy. So that formula will use again. S3 equal to S4, 34.344.4. So at point 3 the entropy is, steam is dry steam, so entropy is Sg only, Sg at point 3 you can say. And S4 at point 4, the steam is not dry but wet steam, but we do not know the dryness fraction of that steam. So this is equal to SF at point 4 plus X4, dryness fraction of steam at point 4, multiplied by SFG at point 4. So these values we can put this one. So the value SF4 equal to 1.3868 plus X4 we have to find out, multiplied by SFG equal to 846, and this SG S3 we got S3 was 6.339, and if we solve this, then we will get the value of X4 is equal to X4, the dryness fraction of steam at point 4 is equal to 0.84. So we will use this dryness fraction value to find out the value of H4. H3 we know H3 is equal to Hg at point 3, but H4 we do not know, that we have to calculate by using the value of X4. So now we can calculate H4 is equal to HF at point 4 plus X4 multiplied by HFG at point 4 enthalpy, 449.19 plus X4, that's now we have calculated 0.84 multiplied by HFG equal to 2237.5, 2328 0.69 kilojoule per kg. So this is H4. If we know what the value of H4, we can immediately calculate the work output, which is equal to H3 minus H4, and that if you put the value of H3 and H4, it will be equal to 46961 kilojoule per kg. By referring the TS diagram, we can say Q in, that means heat supplied in the boiler, is equal to H3 minus H1. So we can put the values. H3 is equal to 3798.3 minus H1. So H1 is equal to the enthalpy of steam at point 1. That means at point 1 the enthalpy is the HF at lower pressure, at the condenser pressure HF1. So this value we have to take for this calculation, that is equal to HF1. So this is equal to H1, enthalpy of liquid, saturated liquid, and that value is equal to 449.19, and that will give us 2349 kilojoule per kg. So this year we have calculated the heat input, or you can say heat supply. So immediately we can find out the Rankine efficiency, that is equal to W out divided by Q in. Out is equal to 469 divided by Q in is equal to 2349. 2349.1, I think, and that is equal to 90.199. So that means the efficiency is 19.9%, the Rankine efficiency. We have to find out the value of power developed if the feed water or steam consumption flow rate is equal to 46.5 kg per second. So let us find out the power developed. We have already calculated that work output is equal to 469.61. Let us write this as like this, kilojoule per kg of steam. And if we multiply this by the 50 kg, the steam flow rate, or we can say the steam flow rate, 50 kg per second. This kg will get cancelled, and that is equal to 211232.45 kilojoule per second. Kilowatt. Joule per second equal to watt. So this much of kilowatt is the power developed by the turbine. So we have calculated both Rankine efficiency as well as the work output, or now we can say it is a power. Work done per unit time is called power. So joule per second is per unit time. It gives us work done per unit time. Okay, thank you.